Another adventure in NMR spectroscopy. I want to look at another aspect of methylene groups, that most problematic little group that we run into, particularly in proton spectra. I've already talked about how methylene groups can overlap badly in NMR spectra, and I'll have a link to that video in the description for this one. I'm responding to the overwhelming demand from, well, nobody really, for a follow-up video. I wanted to look at terminal alkene CH2 groups, methylene groups at the end of a double bond this time, and some of the challenges they will present us with and how we can get around them, particularly using depth spectra and the two-dimensional HSQ spectra. And as is typical, there will be a link to other related videos in the description, and also a link to a PDF file of all the spectra you'll see in case you want a copy of them for yourselves. Now, there are three molecules I want to look at, and the first one is pretty simple, a simple propanol. And here's the molecule and its proton NMR spectrum. Nothing unusual here. We see the pieces we would expect to see. It's a fairly simple little molecule. We see the alcohol group integrating a little bit on the high side, as wet samples often do. We see the CH2 group right next to the alcohol down here, a little over 4.5. It's got the O oxygen on one side, it has the alkene on the other, and of course we see the 3 alkene protons showing all their glorious, lovely, interesting coupling patterns. If we focus in on the alkene protons for a moment, we see the beautiful, beautiful patterns that we expect to see here. And in particular, I want to focus on these two. These two over here are the trans and the cis protons. These are the protons of the terminal alkene. And I want to emphasize one thing here. If you look, it should be pretty obvious from this proton spectrum. Even though these are two protons on the same carbon, these are two very different signals. And it's sometimes instructive to analyze, why are these two protons of this methylene group, the terminal alkene methylene group, why are they different? Whereas in the other methylene group, the one next to the oxygen of the alcohol, why are they equivalent to each other? To do that, we're going to use our dear friend, the plastic molecular model, because I really like using these for this. And in order to see it a little bit better, I'm going to get a little bit closer, extreme close-up, not quite, but almost, coming up. So here it is. Here's the molecule in its glorious plastic form. Here's the methylene group next to the oxygen of the alcohol. And the reason these two protons are equivalent to each other, simply single bonds, free rotation about this single bond here. And if there's free rotation, then there exists, then if you can find one configuration, and here it is now, doesn't have to be the best configuration possible, but there's one configuration, there we go, that puts a mirror plane between these two, then these two protons will be equivalent to each other. Therefore, they will have the same chemical shift and give one signal integrating to two in a proton NMR spectrum. Now consider this set of this methylene group here, the terminal alkene. Now, these two protons are on the same carbon, but even the plastic shows that there's no free rotation. That's a double bond. So it is locked into position here. And no matter what I do over here with the rest of the molecule and its free rotation, there is not one configuration nowhere that I can find that will put a mirror plane right there. It doesn't exist. Therefore, those two protons of the terminal alkene methylene group are different, will have different chemical shifts. They may not be wildly different, but they are going to be different. And in fact, if we analyze the coupling pattern in here, we see what we'd expect to see. Over here at proton A, the most interesting of the coupling patterns, that classic doublet of triplet patterns that we see. If we focus over here, this is the trans proton, trans to group A. And if we measure the coupling constant, it's about 18 Hertz. That's a very large coupling constant. And the pattern that it generates, you could see the doublet. Technically, it should be a doublet of triplets. Doublet because of the 18 Hertz trans coupling. and then a second doublet because of the geminal coupling to its neighbor, the cis proton on the same carbon, and then a long-range coupling back to the CH2 group through the double bond. And if the long-range coupling and the geminal coupling have roughly the same coupling constant, here around 1.7 Hertz, then you get this doublet. It should be a doublet of triplets, but if that small coupling constant is, the two small coupling constants, excuse me, are equivalent, the geminal and the long range, about 1.7 Hertz, then you're going to get a doublet of quartet appearance here. And that's exactly what we see. Over here we see the cis proton. It is a big doublet. It looks like a doublet of quartets. Once again, it's not as widely separated. Here we see about a 10.4 Hertz cis coupling constant, large, but not as large as the trans coupling constant. So here are the, beautifully, here are the two protons of the CH2 group, nicely separated from each other. Now to really dig into this pattern, you take a look at the depth spectra, and they beautifully show just the 3 carbons, and they beautifully identify here at right around 115 ppm the CH2 group of the terminal alkene. So there's our friend, the methylene group that we are interested in looking at carefully. For methylene groups, our other really good friend is the two-dimensional HSQ spectrum. So here's the full spectrum, and you can even see here that the alcohol proton has no correlations. It's a proton not on a carbon, it's on an oxygen in this case. But of course our focus is not the full HSQ, it is on the alkene region. And when we look at the alkene region correlations, there it is at 115 ppm carbon correlating to the 2 protons beautifully. And in fact, even though the HSQ spectrum technically is a considerably lower resolution spectrum than the proton or the carbon spectra, two-dimensional spectra are just so large that we usually sacrifice some resolution. That 18 Hertz coupling constant is so large that we see the crosspeak actually in its doublet form. You could even see it a little bit in the cis, although they're not resolved in the crosspeak, but you can see the crosspeak definitely has like 2 parts and kind of gets a little bit narrower there in the middle. So you can kind of see the doublet nature of both of them here quite nicely. Now I'm going to use this kind of patterning. Sometimes I find students will sometimes find it useful. When we look at it, we have the doublet of the trans, the doublet of the cis, and I have to make be careful about it that the cis coupling constant is larger or smaller, excuse me, than the trans coupling constant, but they're sitting about like this, okay, fairly nicely separated from each other. In the other examples, this changes quite a bit. So let's on to the next one. The next one, here's our proton spectrum of our dear friend pentene. Now I've already done a video going into great detail of the coupling patterns of this thing, so I'm not going to repeat that here. What of course we're going to focus on is its alkene region, and we note it is very similar in many respects to the alkene region of the propanol. Now this time around we see the 2 protons of the terminal alkene of the methylene group there at the end of the double bond, and we see them a little bit closer. I was doing this business a moment ago. There's the trans with the big coupling constant. There's the cis with a large but smaller than the trans coupling constant. They're closer together now. They've kind of moved in something like this. When we look at that area of the terminal alkene, I've had some students look at this thing and say, oh, that kind of looks like a doublet of doublets. And it isn't, and it should be fairly obvious, but I want to emphasize why. Remember, in a doublet of doublets, in a true doublet of doublets, the first and second and the third and fourth parts of the doublet of doublets would have to be exactly the same distance apart from each other. If you have a signal and it gets split into a doublet, and then each of these split into a doublet again, then the first and second and the third and fourth have to be spaced exactly the same. Now, of course, that can vary if depending upon the relative size of these coupling constants, but that's a general rule of thumb for a doublet of doublets. In this particular pattern, if you look at it carefully, the spacing is not the same. And so what we have here is actually the trans and the cis, but they are close together so that, the appearance is a little bit different than it was in the propanol. Once again, our dear friends, the depth spectra, will help us identify the terminal methylene group. It's at 115 ppm, just like it was before. And then, of course, the HSQ spectrum. Now, here's the full HSQ, but our focus is most importantly on the alkene region. And so here is an expansion of just that area of the spectrum. And sure enough, you could see the correlations, the CH2 group of the terminal alkene correlating to these two signals. Now you notice this time around it's a little bit different. You don't see the exact doublet nature anymore because they are closer together, and the HSQ is a lower resolution spectrum. But clearly we have a proton here, CH2 group, correlating to two separate protons. Once again, the two protons are not equivalent to each other, which is a common sort of thing in many different types of methylene groups. It's one of the things that makes the methylene group a complicated one. Here it is in the terminal alkene case. And finally, the last one to look at quickly. This is a natural product. It's eugenol. It's clove oil. And it's a much more complicated proton spectrum. We got aromatic regions in here and other things going on. But once again, we're going to focus on just the alkene region for this molecule. And this time around, we have this OH group kind of sitting here in the middle, but we'll ignore it. And if you look carefully at the integrations, especially over here for the trans and the cis protons, now the signals are not nearly as clean as they looked in the propenol, certainly, and the pentene as well. It's a much more complicated looking thing, and we're running into overlap issues here. In fact, if you look at the integration, you notice they integrate 0.5 and 1.5. It adds up to 2, but what we have going on here is the trans and the cis, and here they are, trans and the cis. In propenol, they were nicely separated, and the pentene, they are closer together. Now they are kind of sitting like this. And so what we have is this one integratable by itself, but it's only half of one of the signals, 0.5, and these are kind of all mashed together, 1.5. That's what's happening in this particular case. And now we use our usual depth and HSQ spectra to really start trying to untangle this one. The depth spectra show everything we would expect to see, again focusing on the alkene region. There's our dear friend right at 115, the terminal alkene once again, shows up very nicely here in the depth spectra. And now the HSQ spectrum shows all the lovely correlations, and focusing on just the alkene region for a moment. There it is again, the peak at 115 ppm, the carbon at 115 ppm, correlating to the two separate but badly overlapped terminal alkene protons of eugenol. To try to tie it all together, I put together this graphic where I stacked the three trans and cis terminal alkene protons from the three example molecules on each other and kind of reference them to one of the peaks, and then so you can see the differences, how in the propenol they are once again nicely separated from each other, and the pentene they're getting closer together, and then finally starting to overlap each other in the eugenol example, okay, where they're over 52 hertz apart in the propenol and down to within the size of the coupling constant here in the eugenol. But the pattern is still quite recognizable, and the depth and the HSQ still allow us to untangle these and see that our methylene group, the two protons, not equivalent by our mirror plane, therefore having different chemical shifts, sometimes quite different chemical shifts like in propenol, sometimes nearly identical chemical shifts like in eugenol, but we can measure it and see the patterns evolving and come to some very definite conclusions about how to interpret these terminal alkene methylene groups. Hope this was interesting and useful in your own work, and we'll talk to you later.